Okay, now we'll take a look at section 12.6, motion of a projectile. In this example, kicker is trying to make a field goal, and given a certain strength, you could determine what angle you need to kick the ball at in order to maximize the distance. Okay, so that might be something we'd want to look at. Here's another application. Basketball is shot at a certain angle. What parameters should shooter consider in order for the basketball to pass through the basket? Well, one would be like the distance, so horizontal distance to the basket. The speed, maybe initial velocity. Could be, if the player is moving. And the basketball location, right? So how high it is and where it is in terms of its height. Okay. The other thing you could consider is the height of the player, right? Okay. In the next example, firefighters using a hose to try to put out a fire, and what parameters would they need to know in order for a RISC computer to determine the angle at which you should aim the water hose? Okay. Well, one, of course, would be the height of where the hose is located. The other one would be the height where the fire is coming out or where they want to aim the hose at. The other would be the initial velocity associated with the water coming out of the hose. Okay. And of course, the distance S, how far away it would be. Okay, so we can handle projectile motion by considering two separate rectilinear motions. One horizontal and one vertical, where in the vertical direction you have gravity, gravitational acceleration, or force of gravity working against the motion. While in the horizontal direction, we basically have zero acceleration. As we go through and solve these problems, one of the things we're going to look at, or one of the things we're going to consider, is that there's no wind resistance. Okay, so the following illustration shows positions of two balls. One's red and one's yellow, where the red ball is just dropped from rest, and the yellow ball has some initial horizontal velocity. Okay. Now, each time, each image, or each picture that's shown is of an equal time interval. So what you notice is that as time goes on, these are all equal time intervals, the distance is further and further, so it's accelerating. Okay. What you also notice from this is that at each time interval, the vertical position is the same. So it's pretty much independent. The vertical position is independent than whatever horizontal velocity is given to the ball. The other thing to notice is that the horizontal position for each point in time is equal. So for every time interval, it travels the same distance, essentially. And that is because there's no acceleration in the horizontal direction, just some initial velocity to start it. The last part of this is just what the question zooms here. What assumption must be made if the movement is through the air? Okay, well, negligible air resistance essentially is it. So there's no force acting against the motion of the projectile in the horizontal direction. Okay, now we have the kinematic equation for vertical motion, right? In this case, it differs from our horizontal motion equation, where we have some acceleration, and this is gravitational acceleration working against our motion. Okay. Well, if we look at the second equation here first to start with, we can see it's essentially the same equation as what we had previously for the horizontal motion, except now we have y and initial velocity y and initial position in the y, along the y-axis. Okay, but here's the third component of this where we have to consider acceleration due to gravity. Okay, and we could actually, if we know point in time t, we could solve for like initial velocity here, and here, we could solve for initial position. And then the last one, if you're not given time, you could actually go and solve for, if you're given like initial vertical position here, you could solve for the velocity at that point in time. Okay. Well, you only need two of these. Essentially, depends upon what's given and what you're looking for. Of course, you could always, if you're given the initial velocity in the y direction, or initial velocity, and you have the angle, you could solve for y too by rearranging this equation. And the first example problem, you have a soccer player who kicks a ball, and you're given some initial information about that, the angle, initial velocity, and you're trying to determine the horizontal distance it travels and the velocity at when it actually, so it goes up, reach some peak, and then it goes back down and strikes the ground at point C. So you're trying to find that velocity at point C. Okay. So to start with, we have the components, the initial, here's like our initial velocity. This is at like point A. Here's our horizontal component of the velocity. So breaking up this into vertical and horizontal components. And here's our vertical component. So now we can write the equations for velocity in the x direction and velocity in the y direction. Okay. And we'll also write down the equations for the position as a function of time, both in the x and y directions. Okay. So you'll notice here that in order for us to determine the actual position, the distances traveled along the horizon, or the horizontal distance, we need to solve for t. Okay. Now, if we look at the equation for the y position, that you'll notice that at this point here, we know the position in the vertical direction is going to be equal to 0. So then we only have one more unknown in this equation, or one unknown in the equation, which is t, and we can solve for t. Okay. And we can do that with the quadratic formula. And if we solve for that, we find that it's at 1.019 seconds. The time when it actually comes back down, it strikes the ground here. Okay, so you'll find that only 1.019 seconds makes sense as a possible answer of the two that you get from solving the quadratic formula. So we have a velocity component in the x direction, which is essentially just our initial velocity in the x direction, since there's no acceleration in the x direction. And then if we go and solve for our y, our velocity in the y direction, where we're actually putting in the value of t that we solve for. If we do that, it comes out to be 5 meters per second. In this case, of course, it's heading down. Then to find the actual magnitude, we just use Pythagorean theorem here to find the magnitude. And that comes out to be 10 meters per second. And the distance, we just substitute in this equation here for t, and we determine the distance is going to be 8.83 meters.